Well, hello, Physics 340 students, quantum students. How are you all doing? So just hope you're all doing well. Hope you're having a good quarter. We're into week 4 now already. Whether you're taking the lab in person or doing the virtually with me, I hope it's working out for you and you're learning some things. You don't always have to be in constant learning mode all the time, but hopefully along the way you're just learning a few things along the way, whether it be about data analysis or how to put a face mask on properly or whatever it is. I hope you're learning a few things along the way. Dr. Rios and I meet every week to talk about how things are going, and we're trying to keep our ideas and our systems and our pedagogy synchronized as much as we can, even though we're in these very different modes. But anyway, let me just focus on the lectures here for a minute. That's sort of what I am in charge of at the moment here. So what we'll do then, we're going to do something a bit different over the next 2 weeks, and then we have sort of like one final experiment. Not for the quarter, but the way we've been going between different experiments every week, cratering, speed of light, Planck's constant, charge to mass ratio is going to be the new one, at least for the virtual students in my lab. That's going to be the last sort of new different experiment like that, charge to mass, because after charge to mass is done, we're going to spend the remainder of the quarter dealing with nuclear radiation counting and things like that, gamma rays and alpha particles and that sort of thing. And that all uses a pretty standard set of equipment, so we'll sort of see a lot of common equipment in the latter half of the quarter. So that's what I mean by sort of the charge to mass is sort of the last different one, okay? And because the experiment charge to mass of the electron is kind of involved, we're going to spend 2 weeks on it, okay, just to make sure that things get done properly and you sort of look at things one more time in a just most proper and thorough manner instead of sort of railroading it over just 1 week. So we'll spend 2 weeks on it. And Dr. Rios and I both have different things that we'll have due and things like that to sort of spread the 2 weeks out and keep it productive and that sort of thing. So just keep that in mind. So we'll be spending 2 weeks on this experiment. But with that, though, the lecture videos that you'll find this week are going to start you down the road of what you're going to need for the nuclear counting stuff. Now, why am I doing that so soon? Well, I sort of have the lectures today, Monday of week 4 to give you, and then next week on week 5, Monday, remember, we have an exam in our class, so I won't have any lectures. I believe the exam then will be our 50 minutes. And so I'm not going to put 50 minutes of lecture videos on top of that. That is going to be your 50 minutes. And so I need to talk to you a little bit about the nuclear stuff today. So the stuff in the lecture that we're doing, that we'll talk about today in lecture on the videos, will only be applicable for that nuclear lab that starts in 2 weeks. Okay, so we'll get a little bit ahead of the game, but you'll get some ideas down. And the thing that is important about the nuclear radiation handling and the data that it comes in is it's a bit new. It's a bit new bend on data analysis. In particular, it's sort of like, what would you do if you're just given a really big list of numbers? I mean, a really big list. Could be thousands of data points, okay? Not the 8 you can squeak out of speed of light, or the 6 from Planck's constant, or maybe the 10 or 15 you'll get from E&M from the charge to mass ratio, but maybe a whole bunch of data points. What are you going to do? Well, you can always find the average and the standard deviation, maybe standard deviation of the mean, the things you know about, but is there more you can do? And I say yes, because when you get a big list of data, it's going to be important to see if there's any patterns in the data. And one of the most basic ways, straightforward ways of getting patterns in data is to look at a histogram. Now, a histogram is a whole new thing in data analysis. It has all these considerations and tie-ins with theories and things. That's very much what the lecturing is about this week, about looking at histograms and what they are and how they work in distributions of data and that kind of thing. Okay, so that's it then for the lecture. So, not very relevant at the moment, but you'll be all ready for week 6 when the nuclear experiments start. Okay, so as far as the charge to mass ratio goes, it is just what we say, the charge to mass ratio of an electron. Not just the charge, not just the mass, but the charge to mass. This is one of the first things discovered about an electron before Miller can figure out what its charge was, and then of course you can back the mass out. So just the ratio is the only thing that we can get out of this week's experiment. So what you're doing, you take an electron beam, scoot it across an evacuated tube in a magnetic field, and of course when charges are in magnetic fields, as you know from physics 133, they start to bend in circles, they start to move in circles. And so if you can determine the radius of that circle as a function of the voltage that accelerates them across the way and the magnetic field that caused them to bend in the first place, you can calculate the charge to mass ratio. The fun thing about this experiment, this is one of the reasons why we're spending 2 weeks on it also, is that there's no clear-cut data analysis mode for this. There's no curve fit that reveals the charge to mass ratio, but you can get a lot of data points from this, more or less kind of economically, easily, as I've mentioned in some previous videos. So hopefully that'll get some ideas across to you about, okay, no clear-cut curve fit, but a lot of opportunity to get some data fairly economically. In other words, it's not that hard to do. So hopefully that's triggering some ideas in your head. But again, the data analysis is not clear-cut. So we're just going to cast you out there on your own to see what you come up with, okay? The demands are going to be the same by the time this thing gets turned in. in my class anyway, we're going to want some writing. Dr. Rios' class, technical questions, but both of us are going to want your best guess, not guess, your best result on what your charge to mass ratio is, plus or minus some uncertainty in that charge to mass ratio. So we're going to let you kind of figure out how to do that. And what we're looking for in this lab is quality and thoroughness. Okay, no one's going to throw their hands up in the air and say, well, this is what I got. You know, investigate some different avenues and see what works the best, but we want quality and thoroughness in the analysis coming up. Okay, and the interesting part about the charge to mass ratio is there's a fairly straightforward equation that drives it. So the charge to mass is a function of three variables: accelerating voltage, the magnetic field, and this radius that the charges make when they're in the magnetic field. And that's kind of the problem. If it's a function of three variables, what are you going to plot? If you wanted to go for a curve fit, what are you going to put on that x-axis? Because it's a function of three different things. Usually the one that has the smallest uncertainty, but yeah, it's not clear. What do you do about the other two? So there may not be anything to linearize, but you can certainly experiment with that a little bit. And so, like, what would you linearize with respect to? Because there's a lot of these independent parameters, and then you have this equation for charge to mass. So if you get a value for charge to mass, what are you going to do about that uncertainty in that measurement, given that it's a function of three variables? Well, you know about error propagation, so that'll be something for you to work on as well. So as you can see, it's probably a good idea that we spread this experiment over 2 weeks, because there's a lot of different things going on, much better than to cram it into 1 week. Okay, so that's basically all I have to say for week 4. I just want to say, you know, I'll see you all on Zoom in my labs. And again, I hope the in-person labs are going well. You're enjoying being in person in Building 180, and hope you're remembering your masks and your face shields and things like that. And, you know, above all that, I just want to wish you a good week 4. Hope your all your other classes are working out well for you. You probably have exams and things coming up. Hope you know, best of luck on all those things. Hope you're all getting out exercising and that sort of thing. And yeah, just have a good week 4, everyone. And I'll see at least my students on Zoom. And of course, any of you can Slack me at any time with anything you need. Okay, so bye for now. Have a good week 4.